We will now start the second chapter of solid mechanics or strength of materials. This chapter is about beams. Now, what is a beam? In all the previous chapter and lectures, we have seen examples wherein we had a bar like this and we were applying force like this. In these cases, all the force which is applied is direct force or longitudinal force. Instead, if we have the condition that we take the same bar and apply force like this, P. This is now shear force or transverse force. Beams are those entities or those elements which are made to resist transverse force. Now, beams by itself is a very large topic, and the subject has to be broken into small parts to understand various things which are there in the beams. Now, the first among them is how to find out the equilibrium of the beam. Now, before we go ahead and see how to find out the equilibrium and or rather the reactions on beams, first we have to see how beam looks like, how it is let's say used in applications and how various forces and reactions get generated in the beam. Now, beam is what is known as a one-dimensional entity. Now, what is one-dimensional entity? One-dimensional means that only the length of the beam is of significance as far as the governing equations of deformation and reactions are concerned. The area of the beam or the area of cross section of the beam, which is this much, let's say it's a rectangular beam like this or a circular beam like that, that area doesn't play an active role in giving the reactions or displacements, etc. to the beam. Of course, the area will come into picture when we figure out the equation for the displacement or the deflection of the beam, but it only occurs as a constant entity there. We will see how the lateral dimensions, rather than area, I will call lateral dimensions, come into picture. But as far as figuring out the static equilibrium of the beam is concerned, the length of the beam is the only one which matters. The area doesn't matter. Let's see how a beam is normally used in various applications. So, we first pay attention to the various civil structures which are around us. If you see, if you pay attention to let's say a bridge. Now, a bridge, you might have seen a bridge is like this. There is a very long, let's say a railway track, and below the railway track there are long columns like this. Now, each of this portion can be considered as a beam because its width and thickness they do not matter. What matters is the length here, and because the track is a very long structure and the other two dimensions are very small, we can neglect them as far as the static equilibrium is concerned. Now in this case, what happens is that there is a force which is acting constantly, which is the weight of the structure. And when a train passes, let's say a train is passing through here, so the train weight will also act here on the track. Now if we take the track alone, the track is having a force which is acting downwards, possibly forces because of the weight of the train which is passing. Now obviously it is rested at these columns here, so what happens is that columns provide it reactions. So if I just simplify this beam, I have a beam which has a weight or a force acting here, and there are some points at which it is rested or it is supported, and these points provide the reaction to the beam. Now these supports here can be of various kinds. Now let's see what kind of supports can be there. So the first support is called a roller support. The roller support is like this, that you have peg, and peg is supported on ball bearings which are in turn supported on the floor, and beam is just placed on the peg like this. So what happens is that beam is free to move this way, but it is not free to move this way. This is not allowed, but this is allowed. And the beam axis here can also rotate like this, which means that the beam can become like that. This is also allowed. Only this vertical motion is not allowed. This is not allowed. So a roller support is a support which provides only transverse reaction. The second kind of support is called a pin support. Now, what is a pin support? In a pin support, we take a pin and the beam, so beam is pinned to the support. So let's say if I zoom this area, I'll have the beam, there's a hole in the beam, and there is a support which is fixed to the earth, and there's a pin here. So it goes and fixes up it. So the beam now cannot go this way, it cannot go this way also, but it can freely rotate about the pin. It can do this. So this pin can provide transverse and longitudinal force reaction. Now there is another kind of support which is called a fixed support or clamp. In this case, let's say that the beam is fixed to a wall like this. This is a wall. So this beam is not allowed to go this way. It is not allowed to go this way. I mean this point of the beam which is just at the fixity, and the beam cannot rotate also. It cannot freely rotate like this. This is also not possible. Now this is known to provide the transverse, longitudinal force reactions as well as moment reaction. Now what is a moment reaction we will see in the subsequent lecture, but as of now just need to keep in mind that these are the three basic kinds of supports which are there for the beam. The first support is called a roller support, which provides only transverse force reaction. This is a transverse force reaction. Pin support is the second kind of support. It provides both transverse and longitudinal force reactions, and the fixed support or clamp, which provides the transverse, the longitudinal force reactions as well as the moment reaction. Okay. Now let's go back to the beam and see how forces and reactions come to the beam. Now let's take a very simple case that we have a beam which is supported on two roller supports, one here, one here. Now we apply a force F on it. Now obviously if I isolate the beam and if I just take the beam as a one-dimensional figure which is like this, and I apply the force F, let's say the beam is has a length L, so and the force is applied exactly at a midpoint. So I have this force F acting at the center, and I have these two reactions coming to the beam. Now please see that these reactions are caused by roller supports, so they can only be transverse, or in this case sort of vertical reaction. Now in common methods of beam analysis, we always assume that the beam is lying along x-axis, which means its length is along the x-axis, and the reactions, the transverse reactions, are always along y-axis. So it is a common practice to follow this coordinate system. And this is y. This is x. I'll just draw it here also. So I just take this. This is x. This is y. Now let's see how this beam equilibrium is attained. Now these beams are always two-dimensional problems unless three-dimensional loading is concerned. But normally in strength of materials, we first study the beams in two-dimensional configuration, which means that the space in which we are working is a two-dimensional space, x and y coordinates, and the beam is a one-dimensional figure in two-dimensional space. Now in two-dimensional space, we can have at most two forces, Fx and Fy, and we can have only one moment which is acting normal to the plane. So there are only three equations of equilibrium in a two-dimensional space. The three equations of equilibrium are sigma Fx is equal to 0, sigma Fy is equal to 0, and sigma m is equal to 0. Now these equations are valid at any point of the beam. So let's see, we apply these three equations to this beam and see what is happening to the reactions. So let's say that this reaction is called R1 and this is called R2. It is just called. So obviously there is no x direction force, so this becomes 0 equal to 0. That's an identity. We just leave it. This equation, this is this equation, this equation will become R1 plus R2 minus F is equal to 0. Now you please see what is happening is R1 and R2 are pointing upwards. They are pointing upwards, while F is pointing downwards. So hence in the equation F has to come as a negative entity. So if we write this equation separating the variables are R1 and R2 equal to F, then obviously we get equation which is a linear equation, R1 plus R2 equal to F. It's a linear equation in R1 and R2, and the sum is equal to F. So using these two equations we cannot solve the problem because we cannot find out what is R1 and R2 separately. So we use the third equation, sigma m is equal to 0. Now what is sigma m? M is the moment of all the forces acting on the beam at a particular point. So let's say that this point is called A and this point is called B. So this is A and this is B. Now let's say that we find out the moment at A, sigma m at A is equal to 0. So what will that give? Now at A, R1 is passing through A, so there cannot be any moment because of R1. So that is out. F is causing a moment which is like this about A. That's a clockwise movement, so it is a clockwise movement. So clockwise movement is always negative, so that becomes minus FL by 2. That is a moment at A because of F. And there is an anti-clockwise movement because of the R2 reaction. So R2 into L, that is equal to 0. So if we do this, we can get the value of R2 which is equal to F upon 2. It's simple, L and L get cancelled. So if we feed in this value here, we get R1 equal to F upon 2. So we get the two reactions, both of them are equal to F upon 2 or half of the applied force. So it's logical also. If a beam is symmetric and there is a load acting exactly at the center, then obviously both the ends will take half the forces. Now let's say that we had seen that the first equation is Fx equal to 0, and we had put two rollers and the beam is on the roller. Now this, we have to see whether this configuration allows the beam to be statically balanced out or statically in equilibrium. It actually does not, because the roller supports cannot provide any reaction in this direction. These are free. But that's not a good condition to have, because in statics, if we do not know what are the forces acting in those two directions, we cannot find out the reactions. But at the same time, both of them cannot be 0 also, because if both of them are 0, that means a small nudge in that direction will make the beam move. So this beam is, even though under that particular force F, seems to be under equilibrium, it is not supported in x direction. So this beam is, or this configuration of the beam and the supports is not something which is desirable or which is generally done. What we do is, instead we take one end as pin, this is the pin support, and one end as roller. Now in this case, there will obviously be one more reaction like H here. This is R1 and this is R2 under the same applied force F, and we will say H is equal to 0. But that will also ensure that the beam doesn't move in this direction. Now this motion is also cancelled out. Hence, if there are two roller supports, that is not going to help you. That is obviously not correct. We have to have one roller support and one pin. This configuration of beam is called simply supported. I can always argue that, okay, instead of one pin, let's have both of the ends as pins. So I take both pins. This is pin. This is also pin. Now, is that a good configuration? Let's check. So I write the equation of equilibrium, Fx equal to 0. I have horizontal reaction here and horizontal reaction here. So H1 plus H2 is equal to 0. And the other two equations are same as this one. But from now we have three equations, this and this. And we have four unknowns, R1, R2, H1, H2. We cannot solve for four unknowns with three equations. So H1 and H2, one of them will be what is known as the unknown entity and unsolvable entity here. So we have to find out all the reactions in terms of either H1 or H2 and assume H1 to be something. Now this makes the problem statically indeterminate, which means that we cannot solve for the values of all the variables using these three equations. In the previous case, it was statically determinate because the three equations were sufficient to solve for 2 or 3 variables. But if you have 2 pins, then it is statically indeterminate because we cannot find out the 4 reactions using the statics equilibrium equations alone. This is also not a desirable condition because this causes problems in understanding how much reaction will be coming, and we have to use advanced methods to solve the problem. Now, let's see another case, which is that of a particular configuration. It is known as cantilever. So a cantilever is like this. We have a beam which is fixed onto a wall here. It's fixed, and we apply a force P here. Now obviously there is only one end to the beam which is supported, so we isolate the beam, apply the force at this end A. There will be a reaction P, or sorry, R, and from equation of equilibrium sigma Fy equal to 0, we will say minus R plus P equal to 0. That means P equal to, or R equal to P. But is that the only thing which is happening? Now let's see, the moment sigma m is equal to 0 about A will lead to PL is equal to 0, but that's not 0 because neither P nor L is equal to 0. So there is a problem here, and if the pin is, or if the support is not able to provide a reaction to this moment, then this beam is going to rotate. It's not in equilibrium then. So the support actually provides a moment reaction to the beam. So let's see how it provides. Now this PL is like this. It's an anti-clockwise moment. So at A, it causes an anti-clockwise moment like this. So if the reaction provided includes a clockwise moment, which is M reaction, I can modify these equations to say PL minus M reaction is equal to E0, which means that M reaction is equal to PL, or there is a reactive moment on the beam which is giving the equilibrium to the applied moment. So the fixed support provides reaction to the forces as well as reaction to the moment, and that's what I had previously told. And in case of roller and pin support, there is no reaction to the moment, but in case of a fixed support or clamp support, reaction to the moment is also provided. Now obviously these are the three basic forms of or rather two basic forms of supports, simply support and cantilever. This is called a cantilever configuration. Cantilever, C-A-N-T-I-L-E-V-E-R, cantilever. Now along with the reaction, the forces can be also of various kinds. Let's see some important forces. The first kind of force is known as a point force, which we have already seen. So we have the beam and it is having a point force here. This is a point force or point load, let's say. There is another kind of force which is possible. It is called a distributed force. So this force, instead of getting at a point, is actually applied over the whole length or part of the whole length of the beam. It's like this. So let's say this length is L dash and the intensity of the force is F, wherein F will mean that, or rather the total force F will be equal to F into L dash. So this is called a distributed force. The distributed force can be uniformly distributed like this, wherein each intensity is equal, or it can be non-uniformly distributed load, which is like this, that its intensity varies like this, something like this. So here it is low, here it higher, again lower, then much higher, then again slightly lower, then much higher, then lower, then slightly more higher, then it is changing like this. In this case, the total force has to be figured out by integrating the intensity over the whole length. This is called non-uniformly distributed load. Besides this, there is another load possible, which is known as the moment load. Now in case of moment load, we can have the moment here, M, like this. This is a very peculiar case of offloading, and we'll see why it is very peculiar. So let's say that this we have a beam which is simply supported. So we have roller support and we have a pin support and we have a moment at the center, let's say L here, or L by 2, sorry, this whole length is L. Now if we find out the reactions, now let's say that there are two reactions, R1 and R2. Obviously there is no moment reaction provided by the these supports. Now we try to write the equation of equilibrium. So sigma fx is equal to 0, this is x and this is y, will lead to nothing because there is no applied force in that direction. So 0 equal to 0. Sigma fy is also equal to 0, but that also leads to 0 equal to 0, which means that there is no applied reaction. Wrong. There are applied reactions. There are reactions to the beam by the supports, even though there is no applied force. So please remember, applied force is different than reactions. So this will lead to R1 plus R2 equal to 0. Even though there is no applied force, there are still reactions at the supports. And why are these reactions there? Because there is a moment applied, and the moment cannot be supported by a moment reaction, so it is being supported by the forces. Now let's do the third one. M about, let's say A, this is A point, is equal to 0. Now this moment is acting at the center, but it is directly transferred to any of the points because the moment is a free vector, it can move anywhere. So this moment is also applied at A. So the moment, now there is a reaction R2, the R2 causes a movement like that, which is also in this case anti-clockwise. So R2 multiplied by L is equal to 0. So R2 is equal to minus M by L, which leads to R1 equal to M by L. Now you see, in both these cases, which means that in case of R1 or R2, the location of M is unimportant, which means that M can be applied anywhere. M can be here at A point, at center of this, here or here or here or here or here, wherever it is. The reactions do not change. And the reason for that is M is a free vector. It can move anywhere on the length of the beam. You can apply the moment anywhere and you can figure out that the reactions remain same, M upon L and minus M upon L. These reactions do not change by the changing position of the moment. Now let's get back to the distributed force. That's another interesting scenario. Let's take the same simply supported beam. So it provides reactions like this. This is R1, this is R2, this is H1, this is a pin support, and at the center we have distributed load of intensity W acting over the length of L by 2 totally. So this is L by 4, then this till center is L by 4, again L by 4 and again L by 4. So at the center half of the beam length, this load is applied. Now to write the equation of equilibrium, we first convert the force into force F here. So the force F is equal to WL by 2, and this is R1 and this is R2. Now here we can simply refer back to the previous reactions which we got for simply supported beam, in which case R1 was equal to F by 2 and that was also equal to R2, because there is no change in the way forces is acting on. So R1 is equal to WL by 4, which is also equal to R2. This is how you solve for the distributed load. Now see, the force was a point force there, and over here it's a distributed force. Even then the reactions do not change. Reactions are still equal, given that the load now applied is symmetric about the center line, which means that the force is or half of the applied distributed load is here on the left hand side and half is on the right hand side. If this shifts here somewhere, then obviously the reactions are wrong. These cases are when the force is symmetrically applied. Now let's see a case where it is unsymmetrically applied. In this case, I just draw a simple diagram here. I have a beam simply supported and a force is applied here, F. This is L1 and this is L2. Here L1 is greater than L2. If you want to figure out what is the reaction in this case, so we just write the equation of equilibrium again, Fx equal to 0, which leads to 0 equal to 0, Fy equal to 0, which leads the same equation R1 plus R2 equal to F, but sigma m equal to 0 about A, this is A, leads to this R2 causes the anti-clockwise movement, R2 multiplied by L1 plus L2 minus F into L1 is equal to 0. So that leads to R2 equal to F L1 upon L1 plus L2. And if you convert that to R1, that will be FL2 upon L1 plus L2. That's an important result in the sense that the reaction R2 has L1 in numerator, and the reaction R1 has L2 in numerator, which means, and the rest two quantities are all constants, F and L1 plus L2 are constant for a given beam. So if we shift the force towards one of the ends or one of the supports, that particular reaction increases, and if when the force is directly over that support, the other support is giving no reaction. So if I put L2 equal to 0, R2 will become F upon F, the total force F, and R1 will become 0, because then the F is directly acting on the second support. So that's an important result. Please remember it, that in case of simply supported beams with a point force applied, it causes reactions which are proportional to the portions of the length which by which the applied force is away from them, because in this case F is further away from A compared to B, it is nearer to B, so reaction at B is higher, R2 is higher, and if it is nearer to A here, then RA will be higher. So please remember this result, it's an important result.